So we have the magnet like this, south, north. So remember, we had a case where we had the radius was changing like this. The radius was increasing and then decreasing, increasing, decreasing, and it was some kind of weird function given by this. So I'm just going to use the same function. So it was, the initial radius was 1.5 centimeters. The final radius was 3.5 centimeters. And the coil was growing in size, but then it was also shrinking, then growing, and then shrinking. So it was a cosine function, and it was negative 1.0 cosine of 2 pi t. So the period of the motion was 1 second. So you went and came back in 1 second, and plus 2.5, and that was centimeters. Okay, so now I want to do another thing. Let's say while that's happening, I'm changing the magnetic field in some weird way. So let's say the magnetic field of the magnet, I'm increasing it some kind of random fashion. Let's say something like this. And we'll make this milliteslas. So when t is equal to 0, the initial magnetic field is 6 milliteslas out of the board. So positive 6 means out of the board. So I'm going to take the view from the right side of the coil. So initially the magnetic field is coming this way, 6 milliteslas. But based on this, excuse me. Based on this function, eventually the magnetic field is going to turn negative, right? As the t gets larger, that means the magnetic field is eventually going to be into the board that way, looking at it. So the magnetic field is doing this weird thing, and then the radius is doing this weird thing. So what is the EMF induced at any particular time? So then you have here, the EMF is negative n d by dt BA cosine 0. So remember, you could change either the B, the A, or one of them, or the angle between them. Changing the angle was the third case we did, where we were rotating the magnet. Okay, so here we're not changing the angle. So the angle is going to be just 0. So cosine 0 is going to be 1. But we are changing both of these. So then we're going to do negative n, and then so we're going to use the product rule. If two things are changing, then we're going to do negative nb dA dt, negative na dB dt. Right, so you just simply apply the product rule, take the derivative of this, right, times that, and then take the derivative of that times this. Then you put the B function that you have, and then the B is going to be that negative 2t squared plus 5t plus 6, and then times 10 to the minus 3. dA dt is going to be, if A is equal to pi r squared, dA dt is 2 pi r dr dt. So that's the dA dt. And then the negative n, A is just going to be pi r squared. And then dB dt is going to be the derivative of this guy, negative 4t plus 5, right? And then also it has a 10 to the minus 3. So now, let's see how that works out. We could factor out the n. We could factor out one of the r's and the pi. Let's see here. Yeah, you know what? Let's factor out a negative n pi r. Then this negative disappears, and then you're just left. And then let's factor out the 10 to the minus 3. Okay, so then we're left with this guy only. And then pi is gone, r is gone, so you're just left with 2. dr dt, and then dr dt is going to be the derivative of that guy. So that's going to be what? 2 pi sine of 2 pi t, and then the derivative of that is just 0. So let's see here, r is gone, okay. And then the negative n, this is gone, pi is gone, and one of the r's is gone. So then you just have positive, and then one of the r's is going to give you that guy, negative cosine of 2 pi t, right, for one of the r's, plus 2.5. Then you're going to have this guy, negative 4t plus 5. And remember, 10 to the minus 4 comes out for the r, because this r is a centimeter, and then plus dr dt is also a centimeter. So then that's becomes centimeter squared. So then you have here the EMF is going to be negative n pi, and then the r function is negative cosine 2 pi t plus 2.5. Then you have here 10 to the minus 3 times 10 to the minus 4. 10 to the minus 7. Okay, then you're going to have here, this is going to be 4 pi times sine of 2 pi t times negative 2t squared plus 5t plus 6, right? Plus this thing. That's probably as simplified as you can get it. Negative 4t times that whole thing. So you have some random looking EMF depending on this one growing and then shrinking, and then the B field changing, you know. So we could find the EMF, for example, at any particular point in time. So let's say at t is equal to, and it could be some random time. Let's say 0.843 seconds. You know, so then you just put everything in, and then the rest is just making sure you don't make a calculation mistake. EMF is, so let's say there is, based on the app that we did, we could do 3 turns. Well, actually, let's say it's not based on the app. Let's make the n large so that we kind of beat this 10 to the minus 7. So I can make the n as large as I want. Let's say 1,000 loops of wire. So then I can make it 1,000. And then pi. Then I could say negative cosine 2 pi times that number plus 2.5 times 10 to the minus 7, 4 pi sine of 2 pi 0.843 times negative 2 times 0.843 squared plus 5 times 0.843 plus 6. So that it all depends on what direction the B field is at a particular time, and then what the area is doing at that time. Is the area increasing, decreasing? So it's a combination of the two. 4 pi sine, and then plus, this represents the rate of change of the radius at that particular time, dr dt, right? So negative 4 times 0.843 plus 5, plus 5. Oh, no, this represents the rate of change of the magnetic field, dB dt. So 0.843 times that times the radius. Negative cosine 2 pi 0.843 plus 2.5. It's a lot of things to keep track of here. So let's so first thing, also make sure you are in radian mode for this one, radian. So we're going to do 2 times pi times 0.843 cosine of that, and negative plus 2.5. So this one came out to be 1.94835. 4, let's say. So 1.94834 times 10 to the minus, well, then you have the 1,000, which is going to make that 1,000 is going to make that 10 to the minus 4. So then you get pi. This expression occurs again over here because it's the same thing. This is the R and this is also R. So then I can just use that again. So you're going to have 4 pi. Then it will occur right there. That same expression will occur. 948,354. Okay, so now let's calculate sine of 2 pi. So 2 times pi times 0.843 sine. Okay, so this was going to be negative 0.834078. That's that. And now this guy, 2 negative times 0.843 squared plus 5 times 0.843 what was that? Oh, plus 6. So then that was times this, 8.793702. So that's that. Plus, okay, and now this term, so plus this term times that term. So we should go like this. So this term is going to be 4 times 0.843 negative plus 5, so 1.628 times that term, which was 1.94834. Well, the rest I could just do it all in one step. Then just multiply this, multiply that. Okay. So 1.628 times 1.948,354. Okay. Minus 0.834078 times 8.793702 times 4 times pi. Okay, so there were a lot more negatives than positives, so the negatives dominated. So the negatives dominate. So I want to make sure that I keep track of the negatives. Then what happened to this negative out there? Did I just forget it? This 1,000 made this 10 to the minus 4. This one was positive. Then you have the pi. Oh yeah, I want to make sure there's a negative outside. So this one came out negative. Then I multiply that by another negative. So I get rid of that negative. See, that was important. Times pi times 1.948,354. Okay, so then the EMF induced 544.7497 times 10 to the minus 4 volts. So then we could go like this and make this 10 to the minus 3. So we could say 54.48 millivolts. So that's pretty noticeable. So you induce a 54.48 millivolts of voltage, right? And what kind of current will that induce? Well, since it came out positive, right? So remember, since it came out positive, the negatives sort of took care of each other. Then it came out positive. Positive means counterclockwise. So as viewed from this right side, the current must be flowing this way, like this. Which means the current that is induced is creating a field in that direction. At that instant, of course, just at that instant. So it all depends what's happening. When the area increases, you tend to already increase the flux that way. So the current induced should be that way to fight against it. So it might have been that at that instant, the area was actually reducing, right? But then it also depends what the B field was doing. So the combination of whatever happened based on what the B was, what the rate of change of the area was, and what the A was and what the rate of change of the B was. So if you keep track of all the signs, they will take care of all that. And then at the end, when you get positive, it will mean it's counterclockwise, like this. So we would say your CCW, counterclockwise. Any questions on that?